Hey guys, so as many of you might already know, I'm building a CO2 laser cutter, and I figured I'd make you guys a video, maybe a couple of videos, just detailing some of the things I'm going through with the laser cutter design. So today we've got the XY gantry, and that's kind of the building block for most CNC systems. So I'm going to go ahead and swivel the camera over and we can get down to it. So there we go. Pan down. I got a whole mess of stuff going on down here. The 3D printer is running in the background. I hope that doesn't interfere with the audio too much in this video. But let's get to it. So this is our XY gantry. And you might be wondering, well, John, why are you making it out of wood? You know, wood's going to expand and contract and change, changing humidity and temperature and stuff like that. And this is just a mock-up, so that's why. And actually the whole actuation system is going to be a little bit different. So I'm not really looking for this design in particular. There are some aspects of this that will be seen in my final design, but some of this is just temporary. So yeah, this is actually really important because it is the building block of the whole system. So what goes into the considerations when we think about designing an XY gantry system for a CO2 laser cutter? So we need to think about what are the specific needs of laser cutting. And laser cutting, the cutting and engraving all occurs in 2D. But many laser cutters have 3D axes. So they've got the Z axis that moves up and down as well. Why would they need that? There's a couple of reasons, two main reasons that you need a Z axis. One would be when you change thickness of material. So if you start out and you're cutting 1/2 inch material and then you pull the board off and you throw another board on and this one's 1/4 inch thick. Well, if you're engraving at the surface of the material. So if I put underneath here, this is roughly 1/4 inch thick. If I put a piece underneath here and I want to engrave that, well, there's a certain distance between the nozzle and the piece. And that's going to dictate, because the lens is at a fixed point in this lens tube. There's a focal point for that lens, and I want that focal point to be on the surface of the material. So if I change the distance that the surface of the material is away from the lens by switching to a thicker or a thinner material, like say this little wrench here, you know, it's less than 1/8 of an inch thick. So I put that in there, well, now I'm farther away, I'm out of focus, there's no way I'm going to be able to do the engraving of the material that thick. So you got to change the distance that the lens is away from the material. Typically, in a laser cutter, they'll move the bed up and down. Now, many other systems, like a CNC router system, would have the nozzle moving up and down. So why don't we do that in a laser cutter? Laser cutter is different. Laser cutters use the bed up and down, move the bed up and down, because weight out here is very significant. A laser cutter can cut and particularly engrave very quickly. And the engraving can take place at speeds of 1,000 millimeters a second. There's 1 meter per second, which is quite fast if you think about it. 1 meter is about, this is about 1 meter in length here. So that just gives you an idea. You can traverse that whole thing in one and just be done. And then it has to accelerate from this side back over to the other side and make another pass. Because with a laser cutter, you can do essentially printing on a laser cutter. And the laser can create a dot, you can snap on and off and put a little dot on the surface of the wood. Of course, it's actually, because it takes time as you're moving to turn the laser on and off, it's actually not a dot, but it's very nearly a dot. You can create reasonably good quality prints that way by just turning the laser on and off and putting a new pixel on on the wood or whatever you're engraving. So you get grayscale or generally like monochrome, 2-color images that way. But with all that switching on and off, you can switch on and off the laser power and then move the laser back and forth. You can print with it, and you want to be doing very high speeds in order to do that, because if you took 1 second for each dot, you can picture in a 1000 by 1000 image, that would take a lot of seconds. So people will often run a high-end laser like this at 1000 millimeters per second. When you do that and you switch directions really fast to go in the opposite direction at 1000 millimeters per second again, there's a lot of forces on here. You can picture catching a baseball. When you catch a baseball, if you catch it in your bare hand, it smacks your hand and it hurts a little bit. If you watched a slow motion video of that, you would see where some of that energy goes. Some of that energy goes into moving your hand and deforming your hand. Some of it goes into heat. Some of it goes out into the air, causes the air to move as well. So all that energy has to be taken care of somewhere. Well, in a motor-driven setup here, we've got multiple motors, and they need to turn a belt. The belt is not on the machine at the time, and that's going to push and pull the laser head back and forth. So when this stops, where's all that energy going? The vast majority of the energy is going back to the motors. And the motors are going to turn it into heat. But the way that the motors turn it into heat is through electrical resistance. So the power supply here is going to send the motors more power in order to overcome that, that force that's being applied against it, in order to stop that, in order to stop this baseball, so to speak, from traveling too far. The motors are going to have to apply more current or more power to the cart. And so in order to stop this cart, it's going to take more the heavier that baseball is. So the more weight we've got on here, just for visual representation, if we had a stepper driver on there, we wouldn't want to put a stepper driver on there because it'd be arbitrarily adding more weight to the system. Or if then we start throwing a Z-axis motor, we got another one of these over there. Now these weigh maybe a pound or two, and you put one of those on there. Well, then suddenly, this is heavier than a baseball, and the thing's got to play with that. The other thing that we're fighting with stepper motors is that a stepper motor runs most efficiently at lower speeds. So when we're pushing the speed of the system, the torque curve actually looks something like this. So as you increase speed, the torque drops. Low speed, high torque; high speed, low torque. So there's a decline in the amount of power that you can get out of the motors the faster they run. So combining all that, basically we want to reduce the weight of this out here as much as we can in order to make it easier on the motors. Now, you should probably know what happens if you overdrive the motors. If you overdrive the motors and they run out of power, you can't run them any harder, then they just fail to stop the cart. Just like maybe a baseball hits your hand, but it hits it harder than you were expecting, and it flies straight back out of your hand. That's a similar thing that happens with the motors. When they're trying to stop the cart and they can't, then the motor just spins backwards. Now, the issue with that, normally there might not be any issue with that, but the issue that you come into with a motor is that these motors are being computer controlled. So there's this controller here. It's a Ruidia controller that I'm using to control this CNC laser. And it's being electronically controlled. So it's sending out over these cables the signals to tell the motor what to do. Basically, It sends it a pulse and it turns just a little bit and it turns just a little bit, and it knows how many pulses that it sent. Well, the motor, because it's electrically sound, it turns the correct number of steps that this tells it to. If it does not, if it actually spins backwards because there was too much of a demand thrust upon it by a heavy head, well then it slips and the controller doesn't know it slipped because the controller is just telling it what to do. It's not receiving, it's not a closed loop system in which it would be receiving signals back from the motor. It's just telling the motor what to do. So you lose position data is what happens. This slides, it goes an extra inch off, well then it continues to print or to cut, and now everything is 1 inch shifted from the first part. So you could have print a part of an image and then have the rest of the image kind of shifted off an inch. And we don't want that. So in order to eliminate that, we don't put another motor on this axis. We put the motor on the whole base, so you can lift, raise, and lower the floor. Now, raising and lowering the floor is a lot more complicated and more difficult than raising and lowering just a single head here. So that's a disadvantage that lasers have over other systems. However, in order to try to eliminate that disadvantage, what I've done is I've gone with a design that does not have a moving bed, but relies solely upon, or mostly upon, the ability to raise and lower the lens tube like this. Now that gets you halfway there. As I might have mentioned earlier, there's two good reasons that you might want to raise and lower the bed, and one is to change the height between materials. So here, say we just push that down onto the material and raise it back up just a little bit so that it's not scraping it. All right, now presumably I've measured and we're at the right height there. Okay, that's good for that material. Well then, when I switch materials over to this one, then I want to adjust the lens tube, and I can just do that by hand, and that doesn't take very long at all. So that's not a big issue. For each time you put something in there, you're going to have to do a setup anyway. You're going to have to clamp it down or line it up where you want it, and just to come out here and you can, with a jig, stick something under there and set it to its right height, clamp it back very quickly. Does not add any significant amount of time to the project, but it can save $100, $200 of cost off of the laser cutter. Maybe more if you account for all the labor involved in setting and calibrating that from time to time. So that's easy enough. But the second reason why you would want to change the nozzle height is that for cutting and engraving, they're two separate operations. Cutting, if this was our material here, the stepper driver, and we wanted to cut through it, then we wouldn't put the focus point on the surface of the metal here. So if you did, what would happen is you have converging focus lines, so the focus of the laser goes like this, but then on the other side it diverges. So it would come in like that at an angle, and then it would go out like this. So what you'd end up with is having enough beam intensity to do your cutting or whatever for maybe the first 1/8 of an inch. But then for the rest of that, your beam intensity would be too low to get the cut done because all the light is expanding, so there's not as much light in that same area. So instead of putting the focus point on the surface, you put the focus point partway through the material so that you get, say, that 1/8 inch above and 1/8 inch below the focus point. Now, different lenses have different focal ranges because with laser cutting, we don't use lenses that are parabolic. Parabolic lenses have a near perfect focus point, and so there's only one pinhead spot where the focus exists. But with a spherical lens, we have something called aberration, which basically means your image would be blurry if you're looking through a camera, or you've got a focal range, so not all the light is hitting one point, it's actually hitting a series of points that are close together. And so that focus range actually acts to our advantage in laser cutting. So the basic idea is for laser cutting, we want to be focused halfway through the material, but for laser engraving just etches the surface. So for laser engraving, we would want to just have the focus distance set right on the surface, laser cutting partway through. That is exacerbated when you increase the thickness of the material, as you might expect. The thicker the material that you've got, the more difference there's going to be between where you want to cut, where you want to focus for cutting, and where you want to focus for engraving. So how do we overcome that issue without introducing a Z-axis? Z-axis means another stepper driver, another stepper motor, maybe some belts, possibly multiple stepper motors depending on how you're driving the thing, pulleys, lead screws, lead screw nuts, all sorts of extra components. So in order to eliminate that and still be able to change the focus for cutting and engraving, I guess one thing that you could do is you could say, okay, well, I'm cutting, so I want to be partway through the material with my focus distance there. Now put a pause, we're going to stop the program halfway through, come back and check on the machine. All right, move that to where we want it. Now we're engraving, and actually you do that in the reverse order. You always engrave first and then cut second. So now we're engraving, and for engraving we just reset the focus distance. Well, that's kind of annoying because you'd rather just be able to cut the whole thing in one go, like all the guys with the Z-axes that can move. So in order to overcome that, what I've come up with is basically this piece here is part of a mirror holding system. And I'll have a secondary lens. So I've only got the one lens tube on here right now, but I'll have a secondary lens tube that sits beside that one. And the light, which comes from a tube in the back, will come up here. It'll hit a mirror over here on the side. That's at 45-degree angle. The light will bounce off of there and come across towards the tube, and then it'll hit a mirror here, which is also at 45 degrees, and shoot the light straight through the lens and down into the material like that. Well, I'll have this mirror holder set up right here at 45 degrees, and it will be plugged into that stepper motor back there. Now this is quite a small little stepper motor, and I've done that because we want it to be small because of the weight. As earlier we mentioned that the weight of this moving across is very important because of the inertia that it carries. That needs to be counteracted by the motors, and at high speed that's kind of an issue for stepper motors. So this piece right here will connect to the stepper motor, and the mirror will be set at its correct location, and then it'll go down this tube for cutting, and when we want to engrave, we just tell the stepper motor to turn the mirror out of the way, and the light will continue to pass through here until it comes to the second lens tube, at which point there'll be another 45-degree angle mirror that's fixed, and it'll shine down onto through the engraving nozzle. And it would do it that way because the engraving nozzle needs to be that much more stable than the cutting nozzle, because the engraving nozzle is going to be the one moving 1,000 millimeters per second. So that's the idea I've got, and in order to do that, I've been a bit concerned that it won't work because this flipper, when it's in its up position, as we do the engraving, could shake and lose steps and then end up sitting right here. And then when the controller tells it to turn to 45 degrees, it'll actually be at more like 60 degrees or whatever, because it shook out of its position while it was engraving. At which point the system would not work. It could shoot light, off over here. It'd be less intense light because it wouldn't be going through a lens, but it could still burn some things, and it would not work, and it might be hazardous. So I want to find out whether or not that's going to work. One other step that I did take to try to increase the likelihood that this thing will work well at 1,000 millimeters per second is using 2 stepper motors for the x-axis here. So I've used 2 stepper motors for a couple reasons. One is, if you use 2 stepper motors, basically you double the amount of torque that you have at those higher speeds, which is great because as we said before, the torque curve goes down like this. As you increase your speed, your torque decreases with the stepper motor. So at those higher speeds, it'd be nice to have that extra torque. Secondarily, if I got extra torque by increasing the size of the motor, getting a more powerful motor, I would run into the same kind of inertia issues. There's a rotor that spins in the middle of these motors, and the bigger and heavier that rotor is, the harder that is to stop. So changing directions at high speed on a bigger motor is more difficult than it is to change directions on a smaller motor. So these smaller motors, having 2 of them, they both have the same rotational inertia, and so this motor will be able to, as a smaller motor, have less of an issue with the rotational inertia. And since they're independent motors, they'll have the same issues with that. Theoretically, a smaller motor is going to be better at handling the higher speeds. So that's what I did here. I've got them wired in series so that they turn in the same direction, and so that I can run them on 48 volts instead of the 24 volts. I've got stepper drivers that are compatible with that. There's some benefit in running them in series because theoretically you end up using less current, and it sounds like the current is one of the main factors for heating up your stepper drivers, if I'm not mistaken. I'm actually a little bit hazy about that at the moment. Yeah, I'll give you guys another update sometime, maybe when I've got the machine running here. A little bit about this Ruidia controller that I don't fully understand how to run yet, but it sounds like it's got some good support and can do quite a bit of things. So yeah, I guess let me know if you like the video, and I'll see you next time. Thanks.